Okay, so what's wrong with this equation? It's ugly. Let's be systematic, like the Terminator. Ready? Pressure. Is that a function of pressure? Viscosity a function of pressure? Z-factor a function of pressure? Anything missing? No. So, function of pressure, function of pressure, function of pressure, of course, sorry, forgot about that. CT is a function of pressure. P over Z is a function of pressure. So what do you think when you see this, Mr. Stone? Sorry? Better know the professor? What kind of an equation is this, class? It is a nonlinear second-order partial differential equation. How do we solve it? Mr. Goins, what's Blasingame rule number 0? Cheat, correct. How do we cheat, class? Nope, we're not going to assume anything's constant yet, Mr. Zanero. You and your habanero wine, okay? Mr. Zanero attempted to put some male hormones in me the other day. You guys are sick. That's disgusting. All right, so now we have pseudo pressure time, and let's see what happened when we use pseudo pressure. We still have C sub T, and we still have mu G. We need to put brackets around this because this is definitely a function of pressure. But no longer do we have a function of pressure on the left-hand side. We now have this new thing called pseudo pressure, and pseudo pressure's definition is given here. How many of you hope you never see this again? All of you, I'm sure. Okay. So this is evaluated at some fixed pressure, and then we take the integral from P base to P of P over mu Z. What are the units? What does this turn out to be? Pressure. That's pretty clever, huh? If you're going to make the chicken think it's a duck, you better make sure the identity crisis is complete. Now, if we also use something called pseudo time, which, by the way, was supposed to be on your quiz today, but I spoke with the quiz master, and I changed that. We're going to normalize with respect to the mu CT product, evaluate 1 over mu GP, CTP, and integrate there. What's the problem with both of these? You must know pressure. It's not so bad with pseudo pressure because that's our variable. That's what we're solving for. But you have to know pressure as a function of time in order to evaluate these things, especially the pseudo time part. Dilhan's sitting in the back kind of scrunching his head because he knows that this is not really true because we've completely linearized the left-hand side. That's what this did. Pseudo pressure linearized the left-hand side. So therefore, we must know pressure as a function of time in order to use pseudo time. Now somebody tell me what conundrum that brings up to us. We must know pressure as a function of time in order to solve this problem, which is a function of time. Uh-oh, this ain't going to work. However, when do we know pressure is a function of time? When we're looking at a response, like a well test. So we could use this pseudo-time formulation for well test analysis. And that's exactly what we're going to do. So that what we're left over with is we now normalize on this, and we have a constant value here. We have the pseudo pressure formulation here, the pseudo pressure formulation here, and now we have a new variable called pseudo time, and the whole thing looks exactly like the liquid equation. Why is this important, Mr. Stone? Because we're going to solve the liquid equation, and if we solve the liquid equation and we make these transformations, then we can use the liquid equation for analysis. In simple terms, my Kazakh row plus, where are you from? Nicaragua? Bolivia? Houston, yeah. Okay. You got your papers?
Yeah.
Okay. Not just yet. I believe you. For now. Okay. So tell me, what does this look like? What does the form on your right look like? We're asking the Kazakhs, okay? Ready? In a moment, when they don't know, we'll ask the Russian. And then when she doesn't know, we'll ask the Coddle. Got any idea? Mr. Coddle? Shall we just jump to you? Or shall we move up? Ms. Fletcher, any ideas? Does it look like the liquid equation? I say yes. Yeah, okay. Do you agree? So if we make this equation look exactly like the liquid equation, we solve the liquid equation, then we can use this formulation. It seems really overwhelmingly boring to talk about this, but every time you run a well test in a commercial software package, I don't care which one, there's going to be a click button that says turn pseudotime on or not. Now, sometimes you don't want to turn pseudotime on, depending on the vendor, because they may do something that pseudotime isn't. How do I explain this in English? Some of them use a model-based analysis, and when you use pseudotime, it's inconsistent with that, but you basically should always use pseudotime. You must always use pseudo pressure. And to you, you're never going to notice any difference. It'll just be a click box. Make sure you use it. Otherwise, you're not accounting for these nonlinearities. If you violate the assumptions of the fluid properties in your analysis, then guess what happens to all your results? They're wrong too. Okay? So, yes, sir. Louder.
When we look at, you're making it look like the liquid equation. Are we taking care of expansion of gas and compressibility? Is that right?
Well, in the liquid equation, we assume the viscosity and compressibility are constant. By defining the pseudo-time function this way, we now have the viscosity and compressibility at a single reference pressure. Good question. So what you're looking at is that piece of N is a reference pressure. It can be anything. I wouldn't make it atmospheric. I'd make it PI because I'm lazy, but that's what I would do. And then once you've done that, it looks, smells, tastes exactly like the liquid equation. So any solution you generate for liquid, the same is true for gas. Now, what little secret did I leave out of this? Get this right, you get an A in the class. Get it wrong, well, you'll have to take the exam next week. Somebody want to take a risk? What about third row? They're far enough back to where they still feel the heat from my blast, but not close enough to feel the shock wave. Mr. Zanero, you want to choose one of your homies, Skype buddies? I noticed you changed your picture. Yeah, who's that hairy guy behind you now? Come on, bring it on. Tell me this. What's missing? For an A in this course, you don't have to come back. I think you'll be coming back. That's factored into the compressibility term. Sorry? No, it's a trick question. Pseudotime, T sub A, is a function of pressure as a function of radius and time. It's not time only. It's a function of radius as well. So, Maybe this, Dilhan, is an opportunity to seek enlightenment. Where are you at? Yeah. Should we ask them to solve this problem for the build-up? Well, we kind of got to wait till after the first exam. Okay? I'm going to erase some things, and we're going to have a quick chat. Since you guys got this problem completely wrong last week, or this week, or every week, let's try this again. Piece of R, log R. Okay? It doesn't matter. Here's PI. Here's some pressure profiles. This is transient, for those of you who forgot. This is 1 hour. This is 10 hours. This is 100 hours. Okay? And we are going to shut in the well at 100 hours. This is rate. This is time. We're producing. We're going to shut in the well at TP equals 100. Okay? You guys ready? So the rate was some value. Now it's down here. Tell me what the pressure profile for the buildup is going to do. This is the drawdown. It's going to go up. Yeah? What's it going to look like? Is the whole profile going to go up? I can't really write it. Let me speak with the hands. Is the entire profile going to go up? Second row. Conk your heads together and come up with an answer. While I'm still young, have a little Congress. Discuss it.
Would your pressure at your boundary come down a little?
Eventually, if it's closed boundary, yeah, but right now we're talking about transient only, so forget about it's as far as you're concerned, it goes on forever. Kind of like your degree, okay? All right, so now we're going to shut in the well, and what's going to happen is this might become the pressure profile at delta T equals 1 hour. What's going to happen to the next one? That'll be delta T at 10 hours. And then the next one. It's not a perfect mirror image. Remember that. Oops, 100, sorry. All right? Why does it backtrack on the last pressure distribution when we shut in? It's going to take a while for it to propagate all the way back out. And so the buildup will retrace the drawdown at the last instant we shut in. Very good. And eventually, if it is depleted, there will sort of switch. But for right now, at time equals infinity, it'll go back to, sorry, I didn't draw that very well. This is delta T equal infinity. Okay, it goes all the way back up. No problem with that, D? All right, so as far as you're concerned, the pressure profile at time 1 hour, the pressure profile at time 10 hours, the pressure profile at 100 hours, they are fixed with radius, yes or no? Yes, they are. They're flat. They rise up. The entire distribution. You can see it on the graph. So what we're looking at is this represents the pressure in the afflicted area, of the buildup. That's the pressure in the buildup. That's the pressure in the buildup. Okay? So that's why we can use the pseudo time integral only as a function of t. This is really stupid stuff. Sorry. This is much heavier. I'm bringing you down. I'm losing you. So let's go on and talk about something fun. Everybody ready? All right. So now let's look at the pseudo time condition. Again, we talked about this before. Is this constant? Yes, no, or maybe. And then when we come over here, it's definitely not constant. The slope is approximately 1. So this is a bad thing. In this case, it's never constant, and pseudo time should always be required. But we're not going to use pseudo time every time. Conditions may prevent it. You can generate this numerically. There is a vendor out there that allows you to simply turn on a numerical model and generate the well test for a gas well case numerically. I can tell you I use it periodically. I always check my analytical analyses with it. Works like a charm. So that's that. We'll cross that bridge for exam 2, but for today's discussion, what I really want you to know is that pseudo time really is always required. Okay? All right. Now, let's look at the pressure squared equations. The derivation of the pressure squared equations is beyond the scope of this course, but maybe not beyond the scope of the exam. Huh, Dilhan? Should we ask them to derive this? No? Why not? You're always the ones that, you quote that Conan the Barbarian line about crush your enemies, have them driven before you, hear the lamentations of their women and children. This would definitely separate the serious from the non-serious student, right? Somebody tell me what the weakest link in this equation is. How can I make this all go away? If I take the derivative of the amount of papayas you have in your house, what do I get? 0. If I take the derivative of the logarithm of the amount of papayas in your house, what do I get? It's the other number. 0. Very good. Okay. The logarithm of a constant is still a constant, right? So, there we got it. If we assume mu z is equal to constant, then this whole derivative, doesn't matter if I'm taking the derivative of the amount of plutonium in your head, it doesn't matter. This whole thing goes to 0. And when that happens, we get this expression. Now, for anybody who's paying attention, and I'm going to walk over to my new Russian friend and ask her why it's so damn hard to get a visa to your country and why you keep wanting to evict me, but then I'm not really telling the truth because I never had any problem going to Russia, okay? Does this look like the liquid equation? Da. Okay, so what? So what happens is we made this major approximation. We assume that mu z is constant. It killed all the nastiness. Guys, creating that top equation is an enormous amount of work. But this is cool because all you got to do is make one simplifying assumption, kill the whole thing. So now that you have an equation that tells you what the assumption is that you have to have in order to make it look like a liquid, you can go investigate the behavior of the mu z product. If you were on a desert island and you only had Microsoft Excel, right? Could you use the pressure squared equation? No, because you would imagine me with a pickaxe in your tent or little hut or whatever it is, probably with a 3-day shave and, in my underwear and a t-shirt going, Mr. Stone, you use pressure squared. I'm the Grim Reaper. Okay, you get the message? You're never going to do that, right? I want you to go to sleep at night and think about that. You're never going to use pressure squared or pressure as an approximation for the gas problem. Why, Mr. Cottle? Because some things just ain't right. In the good old days, if we didn't know how to solve the problem, we made a condition where the problem solved itself like this. But this ain't the good old days. In a minute, you're going to find out what? That the mu z constant is equal to a constant only occurs for what case? P is less than 2,000 psi. Somebody tell me where there's a reservoir in the world where the pressure at initial conditions is less than 2,000 psi. You were raising your hand. I don't know, okay? Anybody? My Kazakh friends. What's that evil empire next door to you? The one that was built around a cult of personality that he was going to live forever? Oh no, that's Nazarbayev. What was the guy's name in Turkmenistan? You remember him? No? You don't care? It's like knowing the governor of Louisiana, huh? Doesn't really matter. It doesn't affect you. Okay. Come on, you guys don't know the leader of Turkmenistan? He died. He declared himself president for life. Then had a heart attack. I guess, what was his name? Turkmenbashi? I mean, he changed his name to fit God of the Turkmen or something. Have you ever been to Turkmenistan? Turkmenistan? Why would you, right? Anybody else? Nobody's been to Turkmenistan? I have a student working in Turkmenistan right now. She's of French Creole extraction. Her mother was actually Chinese, grew up in Reunion Island. She didn't speak a word of Turkmenistani or whatever it is. I'm just kidding, okay. But she learned it and she's on rotation over there. She really likes it because it's basically a medieval empire, right? It's back to the Stone Age, or at least it was. But the entire country of Turkmenistan, as is most of Uzbekistan, is sitting on top of an ocean of shallow gas. And who wants to buy it, class? China, because it's right next door. And how are they going to get their gas to China? They're going to have to go through you. So they're going to have to pay, right? Isn't that how the world works? Does Turkmenistan have a border with China? A little bit, maybe? No? It's got all them other republics. Kyrgyzstan, Tajikistan, things like that. Mr. Cottle, would you go to Tajikistan? No? Even if there's an oil and gas industry there? The other day, somebody asked me if I would go to Kyrgyzstan as a consultant, and I said, for what? You know? And apparently they have some minor, like uranium and gas deposits. I don't know how those two go together, but that's okay. So we're talking about a country sitting on top of a low-pressure gas resource. Mr. Stone over there and you could found I guess it would be, what, Stone Cottle or Cottlestone? Cottlestone. I like that. Cottlestone Gas Company in Turkmenistan. Now you better take about 80% of your money to pay for facilitation, okay? So at any rate, you've created Cottlestone Energy, and you're over there producing gas, and you're going to sell it to the Chinese, and everything's cool, and you're going to use the pressure squared equation. Is that okay? Why? Because it's all low-pressure gas. Now, in the United States, is there a very large gas reservoir on the order of 100 TCF that the discovery pressure was 425 PSI? Tell me the name of it. 5, 4, 3, 2. Nobody? It's been producing since 1920. It's the Hugonon gas field. Wow. So if you discovered a reservoir at 425 psi initial pressure, and you could actually drill a well down to it that made sense, it's only 2,000 feet deep, could you make a living with the pressure squared equation? And if somebody came along and said, I don't want to use the pressure squared equation anymore, I want to use some newfangled fancy equation, would you send all your lobbyists and he-men to beat the crap out of them? Yeah, why? Because using the pressure squared equation is always going to be advantageous for predicting deliverability. So even though it's wrong and over-predicts, as long as everybody's using the same method, even though it's wrong, it's still okay. Dylan, I think I just got another idea for a exam problem. Thank you. When are you're going to post, you're going to discuss the exam problems in recitation Friday, Monday, Wednesday, right? That's what we talked about? We'll go over it on Wednesday of this week in class, and then you'll go over then you'll start going over the guidelines then, right? Okay. All right. And you got to go to your section, okay? Please, because we're going to have too many people. I mean, maybe if somebody has to go on Friday, that's fine, but don't inundate him. Sorry? This Friday, yes. Why, is there a problem? Are you planning to start the chili cook-off early? No? Okay. So now we're going to do the pressure equation, and we have this derivative. And let's go to Mr. Beard. Mr. Beard, if we take the derivative of how many brides' magazines are in your dorm room with respect to, well, it doesn't really matter, does it? Yes. Yeah, Wally told me he had some. Okay. So what's that going to be equal to? Okay. So if we assume that P over mu z is constant, put it in there. It doesn't matter what we're taking the derivative with respect to. It goes to 0, and we're left with this. And by the way, it doesn't matter whether you think this is a little bit wrong or a lot wrong. It's always wrong. The pressure equation never applies, and I'll show you why in about 2 seconds. Why do you think it is, Mr. Stone? Because there is no constant part. There appears to be a constant part up here, perhaps, and this is what Wattenbarger and Ramey said when they looked at this 40 years ago, that was constant. Okay? But you have to go the entire distance. You can't just go in a piece in the depletion. Whatever assumption you have has to be valid for the entire depletion. All pressures. So if you suddenly go from something that's constant to something that's a slope of 1, that ain't going to fly. So the pressure equation, class, is never valid. Forget it. That was easy. No questions. Now, how many of you are going to fall on the floor and start foaming at the mouth when you're looking at this? Dylan, do we require people to derive this in Petty 620? And they like it, right? I can remember all the nice things they said about us. You think you'd like to derive this? No? Why not? Do you remember what this is for? Oh, I got me 2, 3. Tell your mama you'll get your hat back later. You're a pretty smart fellow. What do you think? What are these equations used for? Can you describe the individual terms? No? Okay, you're my hat holder. All right, let's start with the first one. Where's the free gas term? No habla English? Where's the free gas term? Darcy's law for free gas. ¿Dónde está? Right there. Where's the term for getting gas out of oil? There. Where's the term for getting gas out of water? There. Where's the term for getting free gas? There. Where's the term for getting gas out of oil? There. Where's the term for getting gas out of water? There. So red is free gas. It's like Russia used to be before the fall of the Soviet Union, right? They gave away their stuff. Now they've become capitalists, which is kind of cool. Okay. Now, the oil equation, we only have oil itself, and we only have water. Why? Do we have water that comes out of gas? Yeah, but that ain't really going to happen in the reservoir, is it? What are the temperatures? They're extremely high, much higher than the dew point, so that's not going to happen. Are we going to have oil that comes out of water, Kazakh ladies? The right answer is no. Okay, thank you. Are we going to have oil that comes out of gas in a black oil system? Is it a possibility? Is it going to be more of a volatile oil system? Yeah. So the contribution, the likelihood of getting condensed oil out of gas is really small. So for the black oil system, we can take that away. Now you have 3 equations. Somebody tell me the unifying element in these three equations? Sorry? Very good. Pressure. So all we have to do is figure out a way to make these three things and come up with a single differential equation. Okay? How are we going to do that, Mr. Stone? Sorry? More importantly, keep going. Does it make sense to you that if we define a total compressibility function, CT, that captures all of the energy, COSO plus CWSW plus CG, SG plus C sub F, that's all the energy, right? And then if we come over here and we define the total mobility, which is KO over mu O plus KG over mu G plus KW over mu W. There's some magic steps, but if we define those things and apply these equations, what's going to happen? We get a single equation that models it all. Dylan, is this really true? What's not exactly mean? It means no. But under certain cases where the gradient, in particular, what gradient is going to be important here? You can't see it. It isn't listed. What's going to be critical? What gradient is going to be the problem? Sorry? Gradient. No, sorry. What's not listed here? What is the relative permeability a function of? Sorry? Saturation. So somewhere in here, when we start splitting out the pressure terms and these del dot terms, we're going to have a saturation gradient. And this equation, this final result, assumes what kind of saturation gradients, lady? Negligible. What does negligible mean? It means you can ignore it. Okay? Are there any things else that we have to consider? Well, there's also going to be some terms related to the mobility functions, the K functions, and their derivative, and we can neglect those as well. This is a famous paper by Martin, M-A-R-T-I-N. Dilhan, how long is the paper? 3 pages? 2 pages and some junk that ran over on the other side. How many equations? Like 4 or 3 or something like that. And this thing takes how many pages to derive? 20? It's definitely not for the faint of heart. It is in your book in the second text of Lee. If you want to know, that's where it is. So have at it. Okay, now, as Elvis would say, the end is near. And it's time for our little love potion number 9. But before we do that, I want to talk about something else very quickly. We are going to ask you a question, I'm about 100% sure, about taking a solution for the diffusivity equation and sticking it back into the diffusivity equation. This is an exam from 26 March 99. Don't worry, we'll insert this into today's notes. Don't forget to do that. This is the radial flow case. And when we do this, we're going to take PD and we're going to substitute it here, here, and here. So we'll have to take derivatives with respect to R and derivatives with respect to T. You are not going to get this problem on the exam. Let me repeat that. You are not going to get this problem on the exam. But I think you should familiarize yourself with the process of inserting an equation into a differential equation. Okay? By the same token, Dilhan, they are not going to get this one on the exam. you'll notice it's a different differential equation. It is for linear flow. Here's the solution, XD, TD, and you insert it into here, and you insert it into there, and you solve it. Why aren't you going to get this one on the exam? Because we already did it. So we got to come up with a new one. Now you might be smart enough to figure out what my feeble brain's thinking, but if you can work both of these, then you might be able to work that one. But if you think, oh, I'm just going to wait and see what he's going to do before I figure that out, I'm giving you a heads up. I want to see an 80% pass rate on this question rather than what we have last time, 1 person out of 99, you know? I want to see you be able to solve this. So in the true European method, we are going to tell you, you're going to have to be able to solve something like this. We're going to come up with a new solution, though. It might be the Cottlestone solution. It might be the Kazakh solution. You guys want to give me a hand? Send me some advice. What do you think, Mr. Stone? Maybe we could give you the horizontal well solution? Wrong, because it's too complicated. It'd take you 3 days. The radial flow was the first one I showed you. Stay off the crack pipe, okay? Now, so you guys were complaining that I didn't talk enough. Now I talk too much. Quiz time.